All right. So, so the idea here is use matrix vector product to eliminate the sums over A and sums over A and sums over B. Okay. Now allow me just 1 second to go back here and do some bookkeeping. Okay. All right. This is where we are. Okay. So let's look at the first of those integrals and work with it. So what we want to do is write sum over A comma B, and here let me write the limits, okay, because it's useful to remember what the limits are. Remember, the limits on these sums are A and B going from 1 to number of nodes in the element, which for this use of linear basis functions gives us number of nodes in the element equals 2. Okay. All right. So we have this CAE integral over omega c n a comma c twice e a over h e n b comma c dx d b e. All right, this is the one we want to work with. Now, recognizing that number of nodes in the element is equal to 2, right, because we are working with linear basis functions, and therefore we do indeed have 2 of these basis functions in each general element, right, to represent both the weighting function and the trial solution, right. So what this lets us do is the following. This can be written now as the following. We recall that since A and B run over 1 and 2, we can collect the degrees of freedom, the C degrees of freedom, into a row vector using the notation of linear algebra. Okay, and that row vector is C1e, C2e. Okay. Now, what I will also recognize here is something I could have done in an earlier step, is that HE, of course, is a constant because it gives us the length of the element. In many cases, the modulus and the area may not be constant within an element. Okay. But for the simplest case, of course, they are constant, and let me pull them out of the integral by saying that let us now focus on the simplest case possible where those are constant. Okay. So if they are constant, we get 2e a over he. Okay. Integral over omega c. Okay. Now, integral over omega c, we are going to write it out without explicitly, without using the summation. Okay. Instead, what we will do is, recognizing that A and B run over 1 and 2 for this use of linear basis functions, we get a matrix with entries n1 comma c, n1 comma c, n1 comma c, n2 comma c. It's symmetric, but let me write it out in detail here. n2 comma c, n1 comma c, n2 comma c, n2 comma c. Okay, that's the matrix integrated with respect to c. All right. Now, I'll use these parentheses to remind us that this is where to make it absolutely clear actually that that's where the integration ends. Now, just as we wrote C in vector form, right, recognizing that the index A runs over 1 and 2, we can do the same thing with the DBEs, right, recognizing that B also runs over 1 and 2. So that gives us a column vector in the notation of linear algebra, which we will write as D1E, D2E. All right, and I should make a remark here that, or I should make a note that this holds if E and A are uniform over the element omega E. Okay, so for the specific element E that we are writing out this integral, if it holds that the modulus and the area are uniform, we can pull them out of the integration sign, which is what we've done here. Right, we can pull them out of the integral. Okay, HE of course is just the length of the element, and so that's constant. All right, in the general case, the E and A would still be within that integral, and right, we would have written them as functions of C through X. All right, but let's look at this simpler case just for the purpose of brevity and getting to something that we can actually integrate. Okay, all right. So this is where we have things, and now we recall what happens for the special case of linear basis functions. Okay, now recall that n1 of C equals 1 minus C divided by 2, n2 of C equals 1 plus C divided by 2, and that gives us then quite easily that n1 comma C equals minus half and n2 comma C equals plus half. Okay, so we can use them inside there, and so what you're about to see is that in this case the integration is really trivial, because the integrand is a constant, right? And this comes about from the fact that we have linear basis functions. This will not be the case when we extend this to other basis functions, but it's a good way to start understanding how the problem works. Okay, so what that says is that if we look at what we get from that integral that we started out with, it reduces to C1e, C2e twice E A over HE. Now again, note that the matrix is that matrix is fixed, right? It's uniform. It's constant over the element. So we just get here 1/4 from the first entry, which is this entry, right? Recognizing that it's a product of minus half and minus half, we get minus 1/4 here, minus 1/4, and 1/4 again. This 1/4 comes from the product of 1/2 and 1/2, which is from that contribution to the matrix. And so then we just have the integral over omega c, right? Integral over omega c dxc, right? All of this times our column vector of degrees of freedom corresponding to the trial solution. Right. Okay. Now so this is where we are and what we need to do is evaluate that integral. Now that integral, we realize that omega c in this case is recalling that it's a bi-unit domain. Sorry, let me try to make that look like a straight line. Okay, that's a little better, straight segment. Okay. Recall that omega c is this domain, right, in the c space, that being the point 0. Okay, so this integral here is integral -1 to 1 dx, which is just 2. Okay, easy enough. So putting all of this together, what we get is, continuing from that previous slide, that integral that we were working with finally turns out to be C1e C2e. If you look back at your notes, you will see that the 2's in the numerator and the 1/4 in the denominator in the matrix cancel out, and we get E A over HE. The matrix is a really simple one. It's 1, -1, -1, 1. And here we have D1E, D2E. Okay? And recall that this integral emerged from us considering this term, this particular integral in the finite dimensional weak form. Okay? Reduces to this nice, simple matrix vector form. And now you can see why we refer to this as the matrix vector weak form. All right? Just to complete this process, let's also work out for ourselves how things pan out for the previous, for the other integral, right? And that other integral is, well, I shouldn't say likewise, but sort of similarly. Or maybe even similarly isn't right. Let's say in a related manner. Okay. The other integral that we had was the following. Integral over omega c. We had, let me see, what form did we have it in, right? We had integral over omega c. We had here a sum over a, CAE. Here we had NA and FA HE over 2 dx. All right. Again, recognizing that the degrees of freedom corresponding to the weighting function can be put into a row vector, and assuming as well, again, just for the purposes of writing out something that's easy to actually compute, let's assume that these two are uniform over the element of interest. Okay, what that lets us do, okay, so let's say if these two are uniform over the element of interest, we can write this also using this matrix vector form, and in this case we actually just have a simple sort of dot product of vectors effectively. So we have this representation for our degrees of freedom, and we've agreed that we're going to pull F and A out of the integral, assuming that they are uniform over the element of interest. Again, recognize that they're not required to be uniform, right? If they were not uniform, if they varied with position over this element, they would just stay within the integration. Okay. However, we're trying to look at something that's easier to compute in the simplest of entry-level cases. Okay, so we have this, and now we have an integral over omega c, but then omega c we already know has the limits -1 and 1. Okay, and then we have NA back here, but using this vector representation, we write corresponding to N1 and N2, we have N1 here, and we have N2 here. Okay, that dc, right? So that's the integral that we need to compute. And now this is easy enough because we know that N1 is 1 minus c over 2, and N2 is 1 plus c over 2. Okay, so those are the very simple functions that we need to integrate over the limits -1 and 1. Also observe that in here, c is an odd, c leads to an odd integral, right, over the limits -1 and 1. So this is actually, this also works out to a nice and simple form, which is, we have FAHE divided by 2 here, and that integral from -1 to 1 picks up only the constant term. Okay, the linear term being odd vanishes, as you probably know from evaluating these kinds of simple integrals. All right, so that's effectively an integral over half, integral of half over -1 and 1. All right, so we get, in both cases, we get 1. In these two cases, we get 1 and 1. Okay. And this, you recall, came from our original integral in the weak form, which had this form. Okay, so we've arrived at this final form for the forcing function term. All right, this is a good place to end this segment. When we come back, we will talk about what these matrix vector forms give us further.